So, we have already discussed in part 5 about the power in the different types of electrical circuits, including purely resistive circuit, purely uh, inductive circuit, and purely capacitive circuit. Here also, a few more things were left there that we didn't discuss. So, they are to be discussed. So, in the case of the pure resistance, when the current is in phase with the voltage, the angle between them is 0 degree. So, considering the power in the circuit, P is equal to V into I cos theta. So, cos theta becoming cos 0 degree, that means it is equal to 1. So, this is the power P is equal to product of voltage and the current in the circuit. And this power is called, this is very important to remember, that this power is called real power, because this power gets dissipated in the resistance. Whatever material it is made of, the power in the circuit gets dissipated in the resistance itself, the material of the resistance itself. So this is something called real power. You will be able to see the effect of this power in terms of heating. The temperature rise. Uh, so that is it. Uh, it's, uh, this power is perceptible. You can understand that this power is leaving its effect. AC waveform in the case of the pure resistor is like this. The power is positive always, be it negative half cycle or the positive half cycle. In the negative half cycle, as I had told you earlier, that these two, current and voltage, both are negative. So negative and negative multiplied becomes positive. So in the negative half cycle also, this power is positive because it is product of voltage and current both. That's it. And the value of the power is I square R. Now let's take the case of purely inductive circuit. In the case of the inductance, when you apply the voltage in the in a solenoid, then this flux is set in the solenoid, and because of the self inductance, it starts opposing the increase of current in the circuit. So this back EMF produced by the coil is, first thing, that it is because of the self inductance of the circuit, and this self inductance opposes the limits and any changes in the current flowing through the coil. So that is very important to understand why the current is limiting in the case of inductive circuit. The effect of the back EMF is that the current cannot increase immediately through the coil in phase with the applied voltage, causing the current waveform to reach to the peak value sometime after that voltage. So voltage achieves the peak first, as you can see here. The voltage has achieved the peak, uh, voltage has achieved the peak here. Current has achieved the peak at this place. After some time, the voltage has achieved. So this is what that discussion is saying. So in a purely inductive circuit, this XL is 2 pi FL, and the current is lagging by 90 degree, and having a purely inductive circuit. In this case, the power is also the product of VI cos phi, voltage and current multiplied by power factor. But in this case, phi is 90 degree. So 90 degree is 0. So if you look at the power, power becomes 0. So this means uh, there is no power stored in the real value of the power in the inductor is 0. Look at this point. This has been calculated. This is 0. So this does not this volt ampere. This is first of all that it is a volt ampere. In order to show that it is a power of power, but it is zero, it's what is its value? So it is represented in terms of reactive power. So what is reactive power? Reactive power is that amount of the power which is present in the uh, inductive circuit, but it is not, its effect is not visible. So it is measured in volt amperes and it is called VAR, kilo VAR, like this. So volt ampere reactive, VAR is nothing but volt ampere reactive, and should not be confused with watt, that represents the real power, as we had seen in the case of reactive circuit. So VAR represents the product of the volt and ampere that are 90-degree phase apart. They are 90-degree out of phase. And to identify the reactive average power methodically, the sign value is used. This is very important to know. In order to show this, how much is the power, we use sign value because the cos value takes it to zero. So the cost value says there is no power in the circuit. So the inductor, pure inductor, will not consume any power. That figure tells Vi cos phi equal to zero, tells that this circuit is not going to consume any power. Purely inductive circuit is not consuming any power. But if you want to show this power in the circuit, you will have to take the sine value. So it is Vi sine theta. So sine 90-degree becomes 1 and this value is shown as VIR. Like real power, reactive power also depends on voltage and current, but also on the phase angle between them. And it is therefore the product of the applied voltage and the component part of the current which is 90-degree out of phase with the voltage as shown here. So here is uh, mm, power in the inductive circuit. This is your voltage blue line. This is your current profile with a red line, and another is purple color, the power line. So as you can see, where the current is negative but the voltage is positive, the product is negative. So up to this point, the power is negative, and after that it becomes power becomes positive. And also important that in the half cycle, in this half cycle, your power is completing one full cycle. So for the one full cycle of the voltage, this power is completing two cycles. So we had a discussion on this in the earlier video. I hope you are able to understand that. AC power in purely capacitive circuit. Now let's take this one. AC power in purely capacitive circuit. Here this current leads with respect to voltage by 90-degree. So in the capacitive circuit, current is leading. And as in the case earlier case, we had the power to be zero. Here also, Vi cos phi will be zero. So the purely capacitive circuit is not going to consume again any power, right? So it doesn't consume. But when you want to show this figure that it how much power it has, then you take the sine value of that. So it becomes QC equal to V. This is also reactive power, but it is shown as QC. So here QC is equal to V into sine theta and sine minus 90-degree, because your voltage is lagging, current is leading, but voltage is lagging, so it is minus. So QC is equal to V into I minus 1, so VIR, but it is there is a negative sign here. In the earlier case, inductive circuit, it was kept positive. Here it is kept negative. So Vi sin theta has a negative sign. Also, the symbol of the capacitive reactive power is QC with the same unit, volt ampere. reactive. Here, this is also called volt ampere reactive. So there is no difference, but yet there is a difference as the inductor. So VAR is the same, but this is capacitive uh, reactive power. So then we can see that just like a purely inductive circuit in the above case, a pure capacitor does not consume any power or dissipate any real power or true power. So that was the conclusion. So this conclusion has to be kept in mind whenever you are dealing with, capacitive, purely capacitive circuit or real capacitive circuit. So AC power waveform in the case of capacitive circuit is just like this. Blue line is again showing the voltage and red line is showing your current. So as you can see, uh, the positive value of the current is, uh, you know, leading. It is ahead of, it is reaching the peak value before the voltage. So that is why it is called leading. The current is called leading. So here the voltage is lagging. Voltage is achieving its peak value after the current has already achieved. So that is why it is called lagging. All right. That is why we had taken minus 90 degree in the case of uh, uh, capacitive circuit, power calculation of the capacitive circuit, right? Electrical power example number two. So here there is a situation given. One resistance and one inductance is connected in series, and 230 volt 50 hertz supply has been applied on that. So that is causing I current into the circuit. So here is the question. A solenoid coil with a resistance of 30 ohm and an inductance of 200 millihenry is connected to 230 volt AC and 50 hertz supply. Now calculate A, the solenoid impedance, B, the current consumed by the solenoid, C, the phase angle between the current and the voltage applied, and D, the average power consumed by the solenoid. So what is given first, you should, whenever you are calculating something, you just have to summarize certain things. So the given facts are, the data is given is R is 30 ohm, L is 200 ohm, V is 230 volts, F is 50 hertz. Now the A part was saying calculation of impedance. So how to calculate the impedance value? So R is 30 ohm, it is given. You have to calculate XL by using this formula 2 pi FL. So 2 pi into 50 hertz your frequency, 200 millihenry is the value of the inductance into milli, as it is given in milli. So you have to multiply it with 10 to the power minus 3, and that uh, amounts to be 62.8 ohm. So now you can calculate, having calculated XL, and you have been given R. Now you can calculate Z. So Z is equal to square root of R square plus XL square. So substitute these values. 30 square plus 62.8 square is equal to 69.6 ohms. Now you can, having calculated Z, you can calculate the value of I from this equation. I equal to V upon Z. So 230 volt divided by 69.6, this is 3.3 ampere. RMS value, this is giving you RMS value. The phase angle theta is equal to cos theta equal to R upon Z. This is from the formula that we have already studied. So sin theta is equal to XL upon Z, and tan theta equal to XL upon R. So you can use any of this. So cos theta equal to R upon Z, 30 by 69.6, and that is 0.431. If you take the inverse of this value, cos inverse is 0.431, then the angle is 64.5. The corresponding angle to this value is 64.5 degree. As because it is the inductive circuit, the this angle is a lagging angle. That means your current is lagging with respect to the voltage. So average power, AC power consumed in the solenoid is V P equal to V multiplied by I multiplied by cos theta, that is power factor, and this is equal to 230 into 3.3 into cos 64.5 degrees that you have already calculated. So the value of P becomes 327 watt. So that's all in this video. I hope you had a better understanding of all these types of the circuits and the behavior of current and power and voltage and their relative positions in the case of the circuit, different circuits. Uh, uh, so I hope you will appreciate this learning and it will have a positive impact on your understanding, and you can leave your message in the comment box so that I can understand how it helped you. Thank you very much. Stay tuned with me.